afternoon or evening Bearcats. This is 9.1. This is 12.1. Oh my goodness. This is 12.1. It's an introduction to limits. I'm going to say one more Go Bearcats, and I may say a few more during the video, but this will probably be our last instructional video for the year. It's been my pleasure, and hopefully we'll just have new and improved upon videos for next year. So if you're off somewhere and want to tune in, feel free to do so. All right. Anyway, the notion of limits is fundamental to all calculus. So for you college-bound kids who are going off, one of the very first things that you will study in your calculus class is this whole notion of limits. So we want to give you just a brief introduction so that you will have some familiarity with that. So let's talk about three things. We're going to talk about its definition, or by definition. We're going to talk about what is not a limit, or when a limit does not exist. And then we're going to talk about solving limits, or finding limits by direct substitution. All right, let's get started. Okay, here's the definition of a limit. As f of x becomes arbitrarily close to a unique number L, as x gets closer to c, then the limit of f of x, or the limit of the y value, as it approaches x, as x approaches c, as x approaches a particular value, is L. So you can read this. I think visually, this is going to be another one of those visual things and algebraic things that will help you. We're going to look at it from a visual standpoint first, and we're going to look at a table and some graphs before we go to the algebra. I want you to note, though, that the notation for a limit is written as and I'll read this to you, the limit as x approaches c of f of x would equal L. All right, so as x approaches c, then y is equal to L. And we're going to look at that in a table first. So let's take a look at this example based on that definition. As our limit as x approaches 4 for x minus 1. Okay, if we create a table, an x and y table, x and then y, of course, is f of x, our table would go this way. It would be 3.9. As we get closer to 4, it'd be 3.99. Then you would have 4. On the other side, you would have 4.001, 4.01, 4.1, and it would continue to get larger. If we plug in these values and subtract 1, you plug them in, or the table with the y values would give an output of 2.9, 2.99. I'm going to leave a question mark here. 3.001, 3.01, and 3.1. This is a really simple one. So what I want you to read this is, as x approaches 4. Okay, so if we're coming from the left side and we get closer to 4, and we're coming from the right side and we get closer to 4, what is happening to our y value? What is happening to that? As x approaches 4, y is approaching 3. Y is approaching 3. So y is getting closer to 3 as x approaches. So we would write that as the limit as x approaches 4 for x minus 1 is equal to 3, or f of 4 equals 3. Oops, f of 4 equals 3. All right, let's take a look at another graph. All right, let's take a look again at something from by definition. Again, hopefully you recognize this graph. This is a sine or a cosine graph, and hopefully you recognize it as a cosine graph since cosine starts at the top of the amplitude. This is just your basic parent function of a cosine graph. Let's take a look at how we'd write a limit. Our limit of cosine x as x approaches pi. as x approaches pi. So in other words, what happens to this graph as our x values get closer to pi? What happens to the value of y, or our output? So if we take our x values and we move from the left toward where pi is, and we move from the right toward where pi is, then notice our y value is getting closer and closer to -1. So -1 would be our limit. Okay, let's move on and talk about the second topic for today. What happens, or sometimes it's as important to know when a limit does not exist. When a limit does not exist. So sometimes it's as important to know when it does not exist as it is to know when it does exist. Let's take a look. There are 3 very specific times when a limit does not exist. Let's look at the first one, number 1. This is when, and I would take these notes, so if you need to pause and write this down, I would do that. This is when the value of f of x, or you can say the y value, is different as you approach from the right versus the left. Let's take a look at this on a graph. I think it's very visual. So I'm going to give you this piecewise graph. And I'm going to say as x approaches 0, the f of x approaches -1 from the left, and f of x approaches 1 from the right. So in other words, if I'm moving from the left side of this graph, as I get closer to 0, my y value gets closer to -1. As I'm approaching from the right, as I get closer to 0, my y value gets closer to +1. So +1. So in this particular case, no limit exists. Go Bearcats. All right, let's look at a second case where no limit exists. Case 2. Okay, when our f of x, or our y value, increases or decreases without bound. In other words, it continues on forever and never reaches a particular value. Let's take a look at that visually. So let's say your graph looks something like this. So our limit of 1 over x squared as x approaches 0. As x approaches 0. So as x moves closer and closer and closer to 0, our y value moves up without bound. And as our x value moves closer and closer to 0 from the left, our y value moves without bound. So in this particular case, no limit exists. Okay. Third way when no limit, or third case where no limit exists. When f of x, or your y value, oscillates. Hopefully you know that word from from English. Oscillates means move back and forth. It can't make up its mind. If you're oscillating about something, you're constantly changing your mind. You just can't decide. You're going back and forth, back and forth, back and forth. You'll see that in the graph in a minute. Anyway, when it oscillates between two fixed values. Okay, so your graph would look something like this. So it moves, and then all of a sudden it goes down to -1 and up to +1 and down to -1, and it just can't decide. Okay, and it just can't decide. So it's oscillating here in the middle. Now, we would have a limit if x was approaching something like 5 or x was approaching like -10. But in the middle, as x approaches 0, then our y values are oscillating. I should have probably gone a little bit more in here. Are oscillating. So the limit, in this case, for the sine graph of 1 over x, as x approaches 0, then no limit exists. No limit exists. Okay. Let's go on to the third thing I want to talk about, and that is identifying limits through direct substitution. It's more of a little more of an algebraic approach. All right, the last thing we want to talk about, I'm going to give you 4 examples of limits, of finding or identifying limits through direct substitution. This is a little bit more algebraic. We could see that on the graph as our x values get very close to a number, then what happens to our y values. That's basically what's happening. Now, sometimes there could be a hole in the graph, so as it gets really, really close to x, then we want to know what value of y it's getting really, really close to. So it doesn't actually have to have a limit. In the examples I'm going to give you, the limit would exist and it would actually be a particular real number, but as long as it's getting close to that number, then it is a limit. So please let's don't get that confused, and we will talk about that. All right, so our first example of direct substitution would be a limit of x squared as x approaches 4. Well, basically what we would do is we would take our x squared, we would substitute in our 4, so 4 squared would be 16. So the limit of x squared as x approaches 4 is 16. So in other words, as x gets close to 4, our y value would get close, or in this case would actually equal 16. Our limit would be 16. Pause at any time and write this down and think about what I said at your own pace. All right, example 2. We have a limit of tan x over x as x approaches pi. As x approaches pi. All right, well, again, we would plug in our pi for our x value. So we have tan pi over pi. Well, the tan value at pi, if you think about that, your unit circle, the cosine and sine value are -1, 0. 0 divided by anything would be 0, which would be our tan value. So our tan at pi is 0 over pi, which would be 0. So the limit here is just simply 0. All right, 2 more examples. Here's the next one. Our limit of the square root of x as x approaches 9. As x approaches 9. Again, we would come off to the side and say x are the square root of, and we're going to plug in 9 for our x, which would be 3, and our limit would be 3. That one's pretty easy. All right, last one for the day, and probably last example on video for us for this year. Seniors, I wish you all the best in your future endeavors. Juniors, go on and prosper in your calculus class next year, and please come by and see me. All right, here we go, last problem. Limit as x, or of x plus 4 squared as x approaches 3. All right, so we're going to plug in 3 for the x, so we would have 3 plus 4 squared. That's 7 squared, which would be 49. So the limit here would be 49. So if we were to graph this particular binomial, we were to graph that graph, then we would get, which is quadratic, we would get a graph, and as x gets close to 3, our y value would become closer to 49. All right, that's it. Have a great evening, and once again, go Bearcats.